Hello and welcome to part 1 of Dev Maths and Stats Refresher Course, Lecture 9. In today's lecture the focus is on some special distributions of random variables and how these let us move beyond simple descriptive statistics onto inference and estimation. And once you have combined this with a developing understanding of probability, then you have everything you need to start moving on to the kind of statistical tests that we'll develop tomorrow, and then onto econometrics and other techniques you'll learn during the semester. So, to try and illustrate this, I've chosen the example of water pollution. And just to set the scene, with water pollution I've got various scenes from different places. So you can have water which is very, very pure and clean looking like here, with very little pollution. You could have water level which is still very clean but a little bit of algae growth. So it's not quite so transparent, so a tiny bit of pollution. Then you can have much more visible pollution like this, so you can see you're near factories, you can see signs of pollution in the water. Then really, getting quite dirty areas where there's sort of waste going straight into the river from housing. Here, really dirty area right next to outlet pipes would be quite dangerous. And then, worst of all, an area where people still have to take drinking water from and washing water from, incredibly polluted areas. So we're looking at river pollution and a wide range from kind of averagey levels to very, very pure to very, very dirty. And the idea here is we want to work out how would you signpost what the worst areas are. So here I've got a map showing a river system, and we have data from hundreds or thousands of measurements in this river system, in this Excel file. And it actually has 3 different pollutants. So it could be some sort of lead, it could be nitrogen, it could be something radioactive. 3 different kind of pollutants at many places. And what we want to look at is, okay, there's different levels of pollution everywhere, but to focus our resources, which are the ones which are in the worst 5%? So those we're going to say are the danger levels to start with. So locations where the pollutant level is in the highest 5%, we say that's the danger level. We want to flag that up. So in order to do that, we must set the danger level a threshold. So more than that is in the top 95%. Lower than that is in the relatively safe lower 95%. So for each pollutant, the danger level will be different. So we're going to find the data now. I would very strongly urge you to download and work along with this, if otherwise you won't get much benefit from it. So download the danger level.xls file, xlsx I think it is now, and you see what we've got here. This is the whole population of different measurements we have to draw on. So this pretty much covers the entire, so there's 7,000 or 8,000, actually there's more than that. Okay, so there's exactly 10,000 measurements from that, so it's a reasonably substantial set of data with 10,000 rows. And here we've worked out that the mean of this, we're just finding the mean of the whole data set, is 3,474. Standard deviation again is that, so it gives us an idea of the spread. And at the moment I set the danger level to 3,474 parts per million, and this is counting, just counting up how many of these are less than that danger level. So about 4,000, and this is the proportion, because there are 10,000, so 4,976 is 0.4976, just under 50%. So that's not quite high enough. We want to set the danger level so that this should come to 95%, or 0.95. So this needs to go up, so I think it might be more like 3,800. Okay, that's getting there. So please pause the video and find what do you have to put here in order that here you have 0.95. So adjust this and find 0.95. So pause the video while I will go through this. Then when you reactivate it, you'll see if you come to the same conclusion as me. Okay, so I hope you've paused it. I'm now going to try and do this by trial and error. That's not bad. Yes. Might be about as close as you get. Ooh. Yes, okay. So around about there you can get it. Okay, so hopefully you managed to find something like this. It's 3,895.6 is the closest you can get. I think there might be some tolerance there, but this is pretty accurate. 3895.6. Just to show visually that this works, what I'm going to do now is just try and select all this data. You don't need to do this if you want. I'll just demonstrate that. If you select the data and then you just sort it into ascending order, continue, because I don't want to sort the rest of the sheet, just that and those numbers. And I look for this 3895. Now it's in ascending order from smallest to largest, so 3895 I can find is down. Yeah, 3896, 3895 is there. Yes, so you can see it's bang on. So there are 500 higher, and there is 9,500 lower. So it's correctly counted and giving me that idea that I've got the worst 500, the worst 5% are higher than that. Let's just undo that sort. You don't really need the sort. So that's the first one. So 3895.6. So what we're going to do there, if you could just, if you're doing this at home, or wherever you're doing it, what I want here is to record the answer, hopefully. So this is going to be 3895. Oh, let's get the wrong pen. It defaults to giving a square instead of a pen. So the idea is for you to fill in this, and then this, and then this. So that's population 1. Now population 2, we have a very similar thing, so we need to zoom a bit. So here, I want to set the danger level again, but clearly 3895 will be way, way too high because these numbers are all much lower. So you can't put the same thing again. The mean here is 84, so you need to think of something a bit lower that's going to be. So again, pause the video, see if you can find, what should this be? This should be 0.95. So pause the video and then see if you get the same as me. Oops. Okay. So hopefully you find something similar to that. So 94.72, and then for population 3, the same thing again. So what should this be? Again, the levels are slightly different. It's more like population 2 in levels. So pause. What should this be to get 95% here? Pause the video, then see if you get the same as me. So, So eventually, after a lot of trial and error, I got to 205.86. So I hope that you did it quicker than me. So we can enter these on here, which I think I have there. Okay. So hopefully you get numbers according like this. There is some leeway in the decimal places, but here's what you find. So for pollutant 1, 95% are below this, 5% above. Here, 95% below this. Here, 95% below this. So that's the danger level for each pollutant. But so far, it's hard to see any clear pattern there, apart from this must be bigger because this is bigger. So it's kind of related to the level. But I can't see much other pattern. Not really. Next thing to try is looking at the distance above the mean. So this danger level is 421 above this mean here. So I'm just comparing this distance here, from here to here. And that gives some kind of clue, but not really exactly a pattern. I mean, that's way different from that. So no obvious pattern. Can't really see a pattern there. But this is where we start to see something a bit more sensible, where you compare these. So you say, going from here to here, oops, and dividing by this one. So from here to here, how many steps? So going from there to there is about almost 2 steps, about 1.5 steps, if this is 1 step, 1 standard deviation. Going from here to here, okay, that distance, so well, that distance is, you divide that by this. So 9.97 divided by 6.11. So it's about 1.6 steps. And this, how many steps is this? 54 is almost 2 steps. So now we can see there's some kind of pattern here, but not here. So there is some kind of pattern between these two. They are both 1.63 standard deviations above the mean, but this is different. Well, we can get a good insight into where they're different through going back to the original data in Excel and plotting all those populations on a chart like this. So you find this is pollutant 1, pollutant 2, and in those cases we have this very similar pattern. Pollutant 3 does not have the same pattern when we plot all that distribution. And notice that pollutant 1 and 2 have got similar distribution, even though the numbers here are far, far higher. And the numbers here are more similar to these. But these are the ones which have the same pattern. This has a different pattern. And of course, we have a well-known name for pollutant 1 and 2 pattern, which is that they are normally distributed. Pollutant 3 is not. Pollutant 3 does not have a symmetrical distribution. These are symmetrical. This one has a highly skewed distribution. Now, pollutants 1 and 2, we say they are normally distributed. And it turns out, in fact, that 95% of any normally distributed population is this same 1.64 standard deviations above the mean. Now, because of something to do with Excel calculation, we found 1.63. But mathematically, it should be 1.64. So the demonstration is 1% inaccurate. But we find that this works for any normally distributed population. And it's what makes it so useful is it's regardless of the mean, whether the mean is tiny or huge, whether the standard deviation is tiny or huge, this pattern works. And that turns out to be extremely, extremely useful. So for example, if I go back through this again, I say, okay, Let me set the danger level exactly 2 standard deviations for simplicity. What happens now, so I go to here, and what I do this time is, this danger level, I put a formula in here to make it equal to the mean plus 2 lots of the standard deviation. Oops, I've gone to population 3, my mistake. Okay. So it's going to be the mean plus 2 lots like this, it will be about 200 and something. So that gives me 95% below from this one. I'll take the same formula to make it quicker, go to population 2, paste it in there. So you see here, this one is this plus 2 of those, gives me that, so that gives me 97.97% above the mean. And then again, population 1, gives me 97.87, so it's pretty much the same. Yeah. So again, population 1, 2, very similar things happening. Population 3 doesn't work. So now if I go 2 standard deviations like this, in all cases, I get these danger levels, and I find again to 1 decimal place it's identical for 1 and 2. 3 again is going its own way because 3 has a different distribution. So for these ones which are normally distributed, this relationship is very well known. Number of standard deviations you go above the mean tells you the percentage of the population below. So if you know this number, how many standard deviations you are above the mean, you can just find this percentage. It's very well known. You can look it up in all kinds of statistics programs. You look at in the back of every statistics book ever published, you'll find this given, this information. Excel has it built in, or of course you can get it directly by integrating the probability density function between minus infinity and x, and it will give you the correct answer. However, unfortunately it's extremely difficult. So let's use the tables. At which point, if it's a physical class, it's like a ritual. At this point I have to hand everybody in the class, it's almost a law, you have to be given this copy of your statistics tables. So here are statistics tables. So this gives you, what you look up here is what's called Z. This number is called Z, and it's the number of standard deviations you are above the 0. So if we went to our 1.63, we look that up by going to Z is 0, Z is 0.9, 1, 2. So here's the 1.6. To find the 3, actually it's the 4, we'll see. 1.63 or 1.64, you look in the next decimal place here. So you can see that 1.63 has 94.84% less than that, but the closest one is 0.64, which is 94.95. Even though it looks like this one is just as close, but if you look up the next decimal place, this is the closest. So that's 1.64 decimal places above the mean. The other one I showed you was exactly 2 standard deviations, and here's the 97% here that we got from the simulation. So you can look up any number where it goes up to about 3, because when you go past about 3 standard deviations, it's 99.9% is less than that, so it's almost the whole population. So I'll get some practice with using those, and a further example in a minute. Oops. That's the next slide. So we're finished with an example. In some rural area, let's say that monthly income measured in taka per capita is normally distributed with a mean of 1,430 taka and standard deviation 378 taka. From this information alone, you can just predict, okay, what percentage of the population receive more than 2,000 per month? As a sense check, before you dive into this kind of calculation, you should say to yourself, will it be more than 50% or less than 50% of the population? So if the mean is this, and this is 2,000, clearly it will be above 50%. But how much exactly is what we calculate on the next page. Get to the next page. Solution method is, you need to find out how many standard deviations is it from here to here. So you do from here to here, divide by 378, then you can look it up. So the calculation, and so This then, if you like a formula, is your formula for a normal distribution. So x is the number we're interested in working with. So here it's the 2000, that's our threshold. Mu is the expected value or the mean of the normal distribution we're talking about. So here it's the 1430, that's the average earnings, the mean earnings. And sigma is the standard deviation of earnings. So these are the two things we've been given about the population. This is the threshold figure, so subtract and then divide by this tells us that the threshold of 2000 is 1.50794 standard deviations above the mean. So about this much. So the question is, what percentage are less than that? So you take this 1.508. In the tables we can only look up 1.51. So 1.51 in the tables we have to find. So here's 1.5. We see here that 1 is the second column in here. So 1.50, 1.51 is here. So 9345. So 93.45% of people will earn less than that. 93.42. I think I used Excel. 93.42% of people will use less than that. Yeah, 93.45 according to the tables. Okay, I think this 93.42 is, I put all of this into Excel because I was lazy, I didn't use the tables, but the tables give you this accuracy. Don't worry, if you're doing it in a test, you get full marks, whichever you put. By the way, if it is a test or if you're trying to write a report to somebody, if they ask you what percentage of people earn exactly as the question did, if they ask you what percentage earn more than 2000 and you give this answer, yeah, or 93.45, you will get no points, or fewer points, because this many people get less than that, this many people get more than that. So you have to be clear whether you want to know how many are less or how many are more. The tables that we are using here only tell you how many are less. So in this situation, we want to know how many are more. We must do 100, subtract this, leaves this percentage of people. You have more than that per month. So this is called the method of z-scores because we're finding a z-score here. The z-score means the number of standard deviations above the mean you are. And z-scores are often used, for example, in just standard measurements of things like child nutrition. So if you have a child and their z-score is positive, it means that they are above the average for that for the population, the reference population. And you can tell then how you can make a judgment about how far or below they are above the average. So if they're 0.1, 0.2 standard deviations above the average, you say, well, that's normal variation. But if you come with z-score 1.5, 1.6, that means that they're way above. And similarly, if you get a negative z-score, this much means they're way below, so they're very undernourished. So z-scores are a handy way of making those kind of standardized measurements, as well as these kind of direct calculations. Okay, so that's the normal distribution. In the next video, we look at some distributions that are related to the normal distribution. But for now, thanks for watching.